Section 11.3 is called the dot product on vectors. This is going to be mainly used for several applications that we're going to do in vectors in this section and in the next couple of sections. Alright, so first of all, let's define the dot product. So if I have two vectors u and v, the dot product of the two vectors is basically going to represent a scalar. Scalar means it's just a number that represents the product, the sum of the product of their components, meaning the product of the I components, the product of the j components, and the product of the k components, and the sum of those will give you the scalar, which is called the dot product. Okay, and it's represented like just like a regular multiplication symbol, like a dot. Okay. Now, one of the applications we use the dot product into is to find, like if I ask you, okay, we're going to find the angle between two vectors. To find the angle between two vectors, the formula is the dot product of the two vectors, u and v, divided by the product of their magnitudes, which means the magnitude of u times the magnitude of v. Okay, and the cosine inverse of that will give us the angle between the two vectors. So let's start by working on this. Find the angle between the vectors u equals to 6 plus 5j, 6i plus 5j, and v equals to negative 4i plus j minus 5k. So, first of all, let's find their dot product, which is something that we're going to need, because according to the formula, to find the angle between those two vectors is going to be the cosine inverse of the dot product of the two vectors divided by the magnitude of one vector times the magnitude of the other vector. Okay, so the dot product is going to be this. So we're going to have cosine inverse of multiply the I components, which is 6 times negative 4, plus then the j components, which is 5 times 1, plus, and then the k components. The first one doesn't have a k component, that means it's 0, times negative 5, everything over the magnitudes of the two vectors. So, separately, let's go ahead and find the magnitudes of the two vectors. So I'm going to do them right here. So let's find the magnitude of u. The magnitude of u can be found by doing the Pythagorean theorem. So it would be u is equal to 6i plus 5j, so it would be 6 squared plus this 5 squared, the square root of that. So the magnitude of u is going to be 36 plus 25, which is 61. So the magnitude of u equals to the square root of 61, and that cannot be factored or simplified, so we're going to leave it like that. So it would be the square root of 61 times. Now we need the magnitude of v. So let's go ahead and find that first. Magnitude of v equals to the square root of, v is negative 4i plus j minus 5k, so it would be negative 4 squared plus j, which is 1 squared, plus negative 5 squared, which is negative 5k. Then we're going to get 16 plus 1 plus 25. So that would be 42. So the magnitude of v equals to the square root of 42. And 42 still cannot be factored or simplified, so we're going to leave it as this, square root of 42. So then we're going to use the calculator for the rest of it. Let's use the calculator to find the result right here. So we're going to do, make sure your calculator, now depending on what you want, if you want radians or degrees, right now I'm going to get the answer in degree mode. So I'm going to change it to degrees. And we're going to say cosine inverse of, and then on the top we're going to have, I'm just going to put that for another parenthesis for the top, which is negative 24 plus 5 plus 0, right? And then divided by, on the denominator, I'm going to open another parenthesis, and it would be the square root of 61 times the square root of 42 and close the parentheses. And that's the parenthesis for the denominator. Then I'm going to close the parenthesis for the cosine inverse, and that gives us 112.04 degrees. So that means that the angle between the two vectors is approximately 112 degrees. So if I were to sketch them, you will find out that approximately the angle between those two vectors, it appears to be this angle right here, approximately 112. Next. Now on this one, this is an application of the angle between two vectors. So I'm giving you three coordinates. A equals -1, 0, B equals 1, 2, and C equals 1, -1. I want you to find the angles of the triangle whose vertices are these three. Okay, so we don't really need the sketch, but I'm still going to put it just to give you an idea. Okay. So the first vertex is -1, 0. So I'm just going to put a couple of lines here. Okay, -1, 0. This is vertex A. Vertex B is 1, 2. And vertex C is 1, -1. Okay, so first thing you have to do, we're going to find one angle at the time. Okay, so what I suggest you do is this. You're going to give two vectors going, meeting at the angle that you want to find. So for example, if I want to find angle A, the first thing I'm going to draw a vector going from A to B and another vector going from A to C. Okay, and I need to find those two vectors first. Okay, and I'm going to use the same formula we just used to find the angle right here between those two vectors. That's the first one I'm going to find. And then we're going to do the same thing from B to A and from B to C to find the angle B, and then from C to A, from C to B to find the angle C. Okay. First of all, from A to B and from A to C. So if I say, okay, from A to B, what would the vector be? So remember, you just subtract the coordinates. From A to B would be 1 minus -1. It would be 2, right? 2i. And then 2 minus 0 is going to be 2. So it's going to be plus 2j. Then you're going to do from A to C. From A to C, it is going to be A and C. So 1 minus -1 is still 2i. And -1 plus minus 0, it's -1. So minus j. Okay. So then let's go ahead and find the magnitudes of these already. Okay. I'm going to find the magnitude of vector AB and the magnitude of vector AC. So, because we're going to need it for the, and we also need the dot product, remember? So first of all, let's find this. AB, the magnitude would be the square root of 2 squared plus 2 squared, which is going to be the square root of 4 plus 4, which is the square root of 8, right? And we can simplify it, but I don't think we're going to need that, since we're not going to use the simplified version. We can just use the square root of 8 since we're going to put it in a formula. Then, to find the magnitude of AC is going to be the square root of 2 squared plus -1 squared, which is going to be 4 plus 1, and that is 5. Then let's find the dot product. The dot product of AB with AC. Okay, and the dot product is going to be the product of their components, right? And the sum of the product, the product of the sum of the components. So it's going to be 2 times 2 plus 2 times -1. Right? So I'm multiplying the I components and the J components and getting the sum of that product, of those products, and that's going to give me 4 minus 2, which is going to be 2. That's going to be the dot product. So then, to find the angle between the angle A, right? Because it's the angle between AB and the angle between AC, that will be angle A, right? So the measurement of angle A is going to be equal to cosine inverse of, the formula says, the dot product of the two vectors, which is 2, divided by the product of their magnitudes, which is the square root of 8 times the square root of 5. And that should give me the measurement of angle A. Okay, so let's put that in the calculator. So we have cosine inverse of 2 divided by, and then in parentheses, square root of 8 times the square root of 5, and close the parentheses. That gives me 71.56. So what should we round to? Let's go ahead and round to the nearest degree. So that would be about 72 degrees, right? I'm going to put approximately equal because it's not exactly 72. It's close to 72. Next, let's follow the same process, and now we're going to do the same thing to find the angle B and the angle C. So for the angle B, we need to draw two vectors going, starting from angle B. So it would be BA and BC. So an angle vector going this way, BA, and this vector, which is BC. So that's what we have to do to be able to find that angle. So BA and BC. That should give you like the cosine, the cosine inverse of the dot product of these two vectors divided by the magnitude of this vector times the magnitude of this vector is going to give me the angle B, which is the angle between those two vectors. So let's go ahead and find that out. First of all, we need to find BA. What is vector BA? And we need to find what is vector BC. From B to A. So from B to A, if you do A minus B, so it would be negative 1 minus 1, it would be negative 2I. Then 0 minus 2 would be negative 2J. So from B to A, it goes 2 to the left and 2 down. That's why it's negative 2I minus 2J. Same thing with from BC. BC, so we're going to go from B to C. So it would be 1 minus 1, which is 0I. And then negative 1 minus 2 is negative 3J. So from B to C, it is not moving to the left or to the right. It is just moving the J there is no I component, just the J component, which is 1, 2, 3 down, right? So it's negative 3J. Now, let's find the magnitudes of each one. So because we're going to use them for the dot product. So the magnitude would be the square root of negative 2 squared plus negative 2 squared, which is going to be 4 plus 4. And that's going to be the square root of 8. Now, BC. Let's find the magnitude BC. Now, I think we didn't actually need to do it again because AB should have the same magnitude as BA. The magnitude doesn't change if we change the direction of the vector. So the magnitude of that vector is still the same. Okay. So BC, I think we haven't found it, so that we have to find. Square root of 0 squared plus negative 3 squared, which is going to be square root of 9, and that will be 3. Right? Now, what do we need to do next? We need to find the dot product of BA with BC. So it would be negative 2 times 0, multiply the I components, and then plus multiply the J components, which is negative 2 times negative 3. That's going to be 0 plus 6, which is going to give me a 6. Okay. So what angle are we finding here? Angle B, right, which is the angle right here where the two rays, where the two vectors open. So we're going to find the measurement of angle B is going to be the cosine inverse of the dot product, which is 6, divided by the product of their magnitudes, which is the square root of 8 times 3. I'm just going to put 3 times the square root of 8. Put this in the calculator. we can simplify this actually to make it easier. So it would be cosine inverse of 6 divided by 3 is going to be 2. 2 divided by the square root of 8, right? Let's put it in the calculator to find the measurement of angle B, and we're going to make an estimate because we're just going to round it off. So cosine inverse of 2 divided by the square root of 8 gives us 45. So the angle B, it's going to be approximately 45 degrees. Well, in this case, it's exactly 45 degrees. Okay. Now we need to find the angle C. Okay. But since we already know A and B, what can we do? Add them and subtract them from 180, and that will give us the measurement of angle C. Okay. So that's what I'm going to do because it's a triangle. So the measurement of angle A plus the measurement of angle B plus the measurement of angle C has to equal 180 degrees. So we already have A, which is 72 degrees. It wasn't exactly 72, but again, just look at the instructions, and depending on what you need to round it to, that's what you do. In this case, I'm just choosing to round it to the nearest whole number. So 72 plus the measurement of angle B, which is 45 degrees, and then we're going to find the measurement of angle C. So let's add them and subtract it from 180 to find the third. So that would be 117 degrees plus the measurement of angle C equals to 180. Subtract 117. So the measurement of angle C equals to 63 degrees. And we just found the 3 angles. Now you could also have done it with the formula for the cosine inverse, but that would be a way extra work right here. We can also say, okay, I want to find the vectors from C to A and from C to B, and then get the dot product of the two vectors, get the magnitude of each vector, which we already have, because the magnitude from C to A is the same as A to C. The same thing from C to B is from B to C, same magnitude. And then we do the cosine inverse of the dot product of the two vectors divided by the magnitude of this vector times the magnitude of the other vector. That should give us also 63. Well, not exactly 63, but close to 63. Okay. Next. Now this is another application of vectors here. So it says the vector V equals AI plus BJ is perpendicular to the line AX plus BY equals C. Use this fact to find an equation of a line through P perpendicular to V. Okay, so perpendicular to V in the first place, remember one of the concepts of perpendicular that you saw in pre-cal is that you must have the negative reciprocal slope of that vector V. So that vector V, remember the J component is like your Y value, and your X, the I component is like your X value. To find the slope, it would be Y over X, right? So the Y is 1 and the X is -5. This is the slope of the vector V, but I want it to be perpendicular. Okay? Perpendicular means that the slope has to be the negative reciprocal slope. The negative reciprocal of -1 over 5 would be +5. So that's the slope of the line that we're looking for. Now what else? We know that the slope of that line is going to be 5, but also that it has to pass through the point P, which is -1, -8. Let's use the point slope formula to get the equation of that line to begin with. Okay, so what is the point slope formula looks like? It would be y minus y1 equals to m parentheses x minus x1. So we already have the point x1, y1, and we have the slope. Let's substitute them into the equation. So it would be y minus y1, which is -8, equals to m, which is 5, times x minus x1, which is -1. So that gives us y plus 8 equals to 5 times x plus 1. So that gives us y plus 8 equals distribute, so 5x plus 5. And then I'm going to move the x to put it in this. I want to put it in this form, which is the general form or standard form. I'm going to move the x to the other side and the 8 to the other side. So move the 5x over, and the 8 over. So I'm going to do minus 8 to this side and the 5x minus 5x to this side. So you're going to have the following. Negative 5x plus y equals 5 minus 8 is negative 3. However, when you put the equation in standard form, we need to make sure that the x is not negative. The value of x must be positive. So I'm just going to multiply everything times the negative 1. So I can put the x to be negative. So that will be 5x minus y equals to positive 3. This is the equation in standard form. Okay, that equation that equation of that line passes through the point negative 1 and negative 8, and it has a slope of 5, which is perpendicular to this vector, because that vector would have a slope of negative 1/5, which is the negative reciprocal of that. They're perpendicular. They make a 90-degree angle, these two slopes. Next. Now we're going to talk about orthogonal vectors, so perpendicular vectors. So two vectors are perpendicular if their dot product equals to 0. Okay, two vectors are perpendicular if their dot product equals to 0. So, and these are some other properties of dot products that I want you to keep in mind. Dot product is commutative, meaning that the dot product of u and v equals to the dot product of v and u. Okay, the dot product is that it holds the distributive property that u times the dot product of u and the sum of two vectors equals to the dot product of u with one vector plus the dot product of u and the other vector. Okay. Another property is that the dot product of 0 times any vector, it's going to give you 0. Okay. And the next one is that the dot product of a vector and itself, it's going to be the same as the magnitude of that vector squared. Okay. The dot product of a vector in itself, you would realize that it will be the same as the magnitude of the vector, but squared. And the last but not least tells you that if I have the dot product but I multiply it times a scalar c, I can multiply one of the vectors times a scalar and then do the dot product, or multiply the other vector times the scalar and then do the dot product, or first you can do the dot product and then multiply the answer times the scalar. Either way we would get the same result. So this is another formula we're going to talk about, which is the projection of one vector onto another vector. Okay, so if let's say this is one vector u, and I want to see how is it, I want to find a vector that will represent how this vector u is projected onto another vector v. A projection, we're talking about like a shadow. Okay. So basically I want to find the shadow of vector u that will be parallel, that will go onto the vector v. Okay, that's what it means by basically the projection. So to find the projection of a vector u onto a vector v is represented projection of u onto v. V is at the bottom, so it's onto v, is represented by the dot product of u and v divided by the magnitude of the vector that you're projecting it into, which in this case I'm projecting it into v squared, times that vector v. Okay, because why times that vector v? Because I want the vector to have basically the same direction as the vector v, to go along with the vector v, since it is going to be a shadow. Okay, so that's the formula for the projection. Right? let's go ahead and answer the following. Okay. We're going to do this problem, and we're going to answer all the components for this question. For the following vectors, v equals -9 plus j, and u equals -5i plus the square root of 3j, I want you to find the dot product of v and u, the magnitude of v and the magnitude of u to begin. Then cosine of the angle between v and u, then the scalar component of u in the direction of v, so that is given by this, the scalar component of u in the direction of v. It would be the dot product. So if it is the dot, what is it called? The scalar component of u in the direction of v, it means the scalar component is like the dot product. But since it is going in the direction of v, it would be the dot product of u and v over the magnitude of v. Because remember, when I do the v over the magnitude of v, that means it is going in the direction of vector v. Okay, so, and then the projection of the vector u, or the shadow of the vector u onto the vector v. Okay, so first of all, let's go ahead and find the dot product. So for the dot product of v and u, what we do is we multiply the I components and the j components and get the sum of those products. So it would be -9 times -5 plus 1 times the square root of 3. So that would give us 45 plus the square root of 3, and that we cannot add it, so I'm just going to leave it in exact form. This will be the dot product of u and v, because this cannot be added. Second answer, now we're going to find the magnitude of v. That would be using the Pythagorean theorem to find its length. So for v would be -9 squared plus 1 squared. That would be the square root of 81 plus 1, which is the square root of 82. Okay. Now, this cannot be reduced, right? So 82 doesn't have a factor that can be reduced, that can be simplified. So we're going to leave it as is. Okay. Next, let's find the magnitude of u. Magnitude of u would be the length of u, which is -5 squared, plus the square root of 3 squared. And that is going to give us 25, plus the square root of 3 squared is just 3. That would be the square root of 28. Okay. And we already found the answers for letter A. Letter B. Now we're going to find the angle between v and u. I don't know if it wants just the cosine of the angle or the actual angle. I'm just going to go all the way to the angle. But if it's just, I'm assuming that it would all it wants is the cosine of the angle, so not the angle itself. But I'm gonna do both, the cosine of the angle and then find the angle. Okay, cosine of the angle between v and u. You need the dot product of v and u, which is 45 plus the square root of 3 divided by the magnitude of v times the magnitude of u, which is the square root of 82 times the square root of 28. And that is the cosine of the angle. Okay? But then if I want to find the angle, then what I do is I do the cosine inverse of 45 plus the square root of 3 divided by the product of their magnitudes, which is the square root of 82 times the square root of 28. And let's see what that gives us. So the angle theta is approximately equal to, so let's see what this is going to be. Cosine inverse of, parentheses, 45 plus the square root of 3, close it, divided by, open parentheses, square root of 82 times the square root of 28. And that's going to be 12.76. So it's around 13 degrees. So the angle between the two vectors is approximately 13 degrees if we where to sketch them, it will be a very small angle between them. Next, letter C. The scalar component of u in the direction of v. So the scalar component means the dot product of u and v, but in the direction of v means v over the magnitude of v. Okay, that's the scalar component of u in the direction of v. So first of all, we need to find v over the magnitude of v. We haven't found that. So v over the magnitude of v is going to be the same as, we already know v, vector v is equal to negative 9 plus j, right? So it would be negative 9I plus j plus 1j. But we need to divide it by its magnitude. The magnitude of v is equal to the square root of 82. Okay, so that represents basically the direction of the vector v. This is the unit vector that gives v its direction. Okay, so then we're going to find the dot product, which is the scalar component of u in the direction of v, means the dot product of u and the direction of v. Okay, so u, we already have it there, which is negative 5I plus square root of 3j. Okay, so I'm going to put it here. The u is negative 5I plus the square root of 3j. So we're going to multiply the I components, which is negative 5 times negative 9 over the square root of 82, plus the product of the j components, which is the square root of 3 times 1 over the square root of 82. Simplified, this is going to be 45 divided by the square root of 82 plus square root of 3 divided by the square root of 82, and that is 45 plus the square root of 3 divided by the square root, everything by the square root of 82. This is the scalar component, or the dot, which is the dot product of v and the direction, in the direction of u in the direction of v. Last one that we need to find here on D is the projection of u onto the vector v. So that's the last question we need to do. Question D, projection of u onto the vector v. The shadow of u on the vector v, basically. So to find that, the formula for the projection again is the dot product of them divided by the magnitude of the vector v, but squared, times the vector v. The dot product of u and v, we already found it, was 45 plus the square root of 3. Okay, that is going to be divided by the magnitude of v, but square. What is the magnitude of v? The magnitude of v was the square root of 82, but we need to square it. So it would be the square root of 82, but square. And then times the vector v. So we're going to multiply this times the vector v. And that vector v is, again, negative 9I plus j. Okay, so if I multiply this, if I distribute it, well, first of all, on the first part, 45 plus the square root of 3 divided by 82. That's what we get there. We're going to multiply this times negative 9I plus j. If I do that product, then we're going to get negative 9I multiplied times this. It's going to be just negative 9 times 45 plus the square root of 3 over 82I, and then plus the j multiplied times this would be 45 plus the square root of 3 divided by 82, and that is j. And then we can multiply the 9 here. Again, there's nothing that we can simplify. The only thing is that to make it simpler, we can give it in a decimal form to find an estimate, because this is this in exact form, this is as far as we can go. Okay, but I can also write it like this. Plus the square root of 3, that divided by 82. So that gives us negative 5.1 approximately. That's about negative 5.1 I plus, and then we can do the same for the other one. 45 plus the square root of 3, I forgot to open parentheses, but I'm going to put enter, divided by 82. That gives us 0.6. So plus 0.6 j. So that would be approximately what the projection of the vector u onto the vector v would be, the shadow of the vector u onto the vector v. It would go in this direction and it would have these values, approximately. Okay. Now this is one of the applications of basically vectors also, is finding work. If you remember from physics, the formula for work is force times distance. In this case, it's basically going to be the same thing, but dealing with vectors, we're going to call it the dot product of the force and the displacement, or the distance. Okay. So if I'm doing some work pushing an object, then to find the work, I'm going to multiply the dot product of the force that I'm applying to pull or push something, and the distance vector, basically the distance in the direction in which I'm pushing it or pulling it. Now, before we get to that, we're going to do some easy applications of what we did on the previous section. This is a gun with a muzzle velocity of 920 feet per second is fired at an angle of 23 degrees above the horizontal. Find the horizontal and vertical components of the velocity. So we kind of did this. So we're going to shoot it at an angle of 23 degrees above the horizontal. Right? And the magnitude of the velocity of that gun is going to, of that shooting, is going to be 920 feet per second. That's the velocity in which it is traveling along this vector. Okay, so that's the magnitude, right? So now what I want is to find the horizontal components of the velocity, which is this, and the vertical component of the velocity, which is this. Remember, the formula to find the horizontal component is going to be the magnitude, which is 920, times cosine of the angle, which is 23 degrees. And to find the vertical component of the velocity would be the magnitude, which is 920, times sine of the angle, which is 23 degrees. Okay? So let's find those estimates using the calculator, and let's go ahead and round it to, let's say, 1 decimal place. Just like, well, this one is rounded to the nearest number. So let's round to the nearest whole number as well. So 920 cosine of 23 degrees, that is 846.9, which basically, if we round to the nearest whole number, it will be 847. So I don't know what should be best. Let's round to 1 decimal. So 846.9. So feet per second, right? Horizontally, that's the velocity in which it's traveling horizontally. Okay. Now let's find the velocity in which it is traveling vertically. So 920 times sine of 23 degrees, that is 359.5. 359.5 feet per second. So what are the components of the velocity? Remember, we're going to write it in component form. it would be 846.9, comma, and 359.5, and close the bracket there. So that's the component form of the velocity of that vector. The horizontal component, comma, and the vertical component. Next, we have two more things to do. So first of all, let's apply the let's answer this question. Suppose that a box is being towed up in an inclined plane as shown in the figure. Find the force W needed to make the component of the force parallel to the inclined plane equal to 2.5 pounds. Okay, so first of all, what we need is we need to think of this as follows. Let me make this bigger so I can show it to you better. Okay, so right here, as you can see, that we want to find, all they're telling us is that the component of the force parallel to the inclined plane is 2.5, meaning that if this was a 15 degree right here, if this was a 15 degree angle, then that force right here of this vector, like applying the force through this vector, would be 2.5 pounds. Okay, that would be the force there. It would be 2.5 pounds. But then, what we want to find is we want to find the force that is being applied at this angle of 36, so that this component equals to 2.5. So, if that component equals to 2.5, what else can we say? We could take this 2.5 with this vector as if it was my horizontal component of this vector right here. Let's assume it to be the horizontal component. And so that angle would not be 36 anymore. So if I get the difference of 36 minus 15, this angle would be an angle of 21 degrees, right? Okay, 21 degrees. So if I want to find, if I know that this horizontal component is 2.5 and this angle right here is 21 degrees, how do I find the horizontal component of a vector? To find the horizontal component, you do the magnitude of the vector, which in this case we're going to call it vector W, times cosine of that angle between them. In this case, that angle between the horizontal component and the vector is 21. Okay, that should give me this horizontal component, which is, we already know what that horizontal component is 2.5 pounds. So all we gotta do, okay, we already know what the angle is. So the angle is 21 degrees. So that's cosine of 21 degrees. So that means that the magnitude of this vector W times the cosine of 21 degrees equals to 2.5 pounds. So how do we solve for this? We just need to divide by cosine of 21 degrees to solve for the magnitude of that vector W. And that's what we're looking for. So then we're going to divide 2.5 divided by cosine of 21 degrees. That gives me 2.7. So that would be 2.7 right there. Okay, so then that's going to be the magnitude of that vector W. So we're going to say that's approximately, I'm not going to say equal, but approximately equal to 2.7 pounds. Next, this is the last question here on this section. We're going to find the work done by a force of 9I, magnitude of 9 newtons, because it is only going in one direction, right? So if you get the 9 squared plus 0 squared, which is my J component, it would be 81, which is the square root of 81 gives me 9. So 9 newtons is still the work, so I mean the force. So it doesn't change, right? Because it is only going in one direction, so that same value is the magnitude. So in moving an object along the line from the origin to the point 2, 2. So if I move it from the origin to the point 2, 2, let's call it vector v. Well, I'm going to call it the displacement vector. Okay, the displacement vector or the distance vector. So what would the distance vector be from here to here? So if it is from the origin all the way to the point 2, 2, it would be 2I plus 2J. And this force vector, it is going to be 9I plus 0J. Right? The force is just being applied in the horizontal direction. So if I want to find the work applied, it will be the dot product of the force and the distance vectors. Okay, so that would be the dot product of the force and the distance. Let's multiply the I components, which is 9 times 2, plus, and then the J components, which is 0 times 2. That would be 18 plus 0, which is 18. So that means that the work applied to move from the origin to the point 2, 2, using the force, horizontal force of 9I, then it would be 18, and it would be Newton meters or Newton units. In this case, we're going to call them joules, the work. Okay, newtons times whatever measurement of distance, it will be, we're going to measure it into joules. Okay, and this problem concludes section 11.3.